So here are the results from a previous year's experiment, and you can see here that we've got the distance from the source, the counts in 100 seconds, the counts in 100 seconds take away the background count in 100 seconds, and then we've got LND and LNC, and the LNC values are the natural log of the counts in 100 seconds take away the background count. We always need to take away the background count before we do our analysis, so if that's not clear on the table here, that's what it is. Okay, so what we're going to do now is have a little look at this graph. So this is the graph that I've plotted of the natural log of the count rate, and remember this is the count rate minus the background count that I've natural logged here, and the natural log of the distance from the source to the detector. So I've plotted my points here, and as you can see it's a roughly straight line graph with a negative gradient. So those are plotted directly from the points in my table, from the data in my table. What I can do now is obviously plot a line of best fit. Okay, so I'm going to draw a line of best fit. Now, to do that, obviously I need to line up my ruler as usual. Okay, and I'm going to do this with a pen, which is always dangerous, but it shows up better then for you when you see it on the video. Okay, so there's my line of best fit. Okay, now I then need to calculate my gradient. Now what I'm going to do here is I'm going to make my gradient triangle from here, from this point here over to here, and then from there up to there. So that's going to be my gradient triangle. Whenever calculating the gradient, you want to make your gradient triangle as big as possible, okay, because it makes your calculations more accurate. So let's start off then with the delta x value, so the change in x here. Okay, and I'm going to write it down the bottom here so that the examiner could see what I'm doing, and they can then see hopefully that this is my gradient triangle, because it's not easy to see because it actually forms part of the axes. So delta x over here, this is 4.1. Okay, that's 4.1 and that's 3. So it's going to be 4.1 take away 3.0, and that obviously equals 1.1. So there's my delta x value. Now my delta y value, the initial, remember when we do change in x, we do the final value take away the initial value. So we're doing the change from here to here. So the final value of x here is 4.1 and the initial value was 3. Now if this is the final value of x, then the final value of y is the corresponding value at that point, which is 3.2. So delta y here, okay, is going to be equal to 3.2 take away. So that was my final. I'm working out the gradient between these 2 points essentially, aren't I? Okay, and that's my final value of x. That's my initial value of x. So my final value of y was 3.2. My initial value of y is 5.4. And if you look carefully here, each of these little squares is 0.02. So that point there is 1.5 little squares. So that's 0.03. So it's 3.20 take away 5.43. Okay, and if you work that out, that's going to give you 2.23, but it's a minus value. Okay. Now that's important because obviously the gradient here is negative, so if you get these the wrong way around, you'll end up with a positive gradient. So then you can work out the gradient. So the gradient now equals delta y over delta x, which is equal to minus 2.23 over 1.1. And if you calculate that on your calculator, you're going to get minus 2.03, which is slightly different to when I did this on the Excel graph that you can see on the PowerPoint, but very, very close. And it just shows that, you know, a slight change in your gradient, you might not draw your gradient, you might not draw your line of best fit quite the same as mine, so you may get a slightly different value from me. As long as it's close and your gradient is reasonable, your line of best fit is reasonable, then that is absolutely fine. Okay, there we go. So that's that. Now the next bit then is that we now need to work out the intercept, but the problem here is because we haven't plotted 0 on the x-axis, that's not our intercept, so we can't calculate the intercept on this graph by just taking the value where the line of best fit hits the y-axis, because it's not hitting the y-axis when the value on the x-axis is equal to 0. So to work out our intercept, we need to take some values from our graph, and I'm going to pick a point here. So I'm drawing across from my y-axis to the line of best fit, and then I'm drawing down to my x-axis here. Okay, so what you can see here is when the value on the y-axis is 3.4, the value on the x-axis is 4. Sorry for this mess that I've made here. That's the problem with doing a graph in pen. So we know now that the value on the y-axis is 3.4. At the same time, the value on the x-axis is 4.0. So knowing that now, we can calculate our value for the intercept. So we'll do that next. Okay, so we're now going to calculate the intercept. We can use this equation, lnc equals lnk plus n lnd, and we can just rearrange it to get lnk equals lnc minus n lnd. Okay, now we know from our graph that when lnc equals 3.4, lnd equals 4.0, so we just need to put these numbers into this equation to get lnk. So lnc is 3.4, and we're going to minus, now we know that n is equal to minus 2.03. We've already worked that out, that's our gradient from our graph. So we're going to do lnc minus minus 2.03 multiplied by 4.0, okay? And that's going to give us our value of lnk. Now you're just going to do 3.4 minus 2.03 times 4, and that's going to equal 11.52. Okay, so there's your value for lnk. Now we want to work out k. Now if we know lnk, then to get k, we know that k is equal to e to the power of lnk. Okay, so k is equal to e to the power of 11.52. So that's going to be equal to 100,710 when you round it up. Okay, so that's our value for k. So we now know a value for n and a value for k, and then we can use that to rewrite the equation. So we know that c equals k d to the power of n. So you can now substitute these values into this equation to get c equals 1,710 d to the power of minus 2.03. That's what you might be asked to do in an exam. Okay. Now you may also be asked, does your graph confirm this equation? Or maybe you might be asked, does your graph confirm this equation, more to the point? Okay, you might be asked to say, does your graph confirm this equation? I would say yes, because you can rewrite this equation as c equals k d to the power of minus 2. So we know that our value for n here should be minus 2, and it is minus 2. Okay,